of which we've been following all through this lockdown. Thank you very much for already quite a lot of people here of attending our regular Thursday colloquium that we've been having for many months now, exactly at the same time. And we, as you know, are also streaming you on YouTube Live. So there are several people there at the same time watching. Very, very happy to welcome Sumanta Chakraborty, who's one of our star students of IUCAA. So he's started his career here at IUCAA working with Professor Padmanabhan, and then not so long ago went back to Kolkata and joined the Indian Association for the Cultivation Science, where he's joined very recently as faculty. And he is going to talk about the cosmic censorship conjecture. As people who are regulars in this program know that what we normally do is we keep the questions till the end. And so at the end, you will, if you haven't done this before, the participants window has a hand raising button, which you can raise your hand and we'll let you ask questions right at the end. But before then, welcome to Sumanta, welcome back.
Yeah, thank you, Somok, and thanks to Kandhu as well for giving this opportunity. And yeah, it's a pleasure to give the talk at IUCAA. But of course, it's a completely different experience giving it from home through an online platform rather than giving it in Vaskara 3. But fortunately or unfortunately, earlier in the talks, there are very little attendance, but it's very nice to see that in the online colloquium, at least there are quite a large number of people listening to this theoretical kind of talks. So as Shomak mentioned, I will talk about the strong cosmic censorship conjecture, and in particular, it is divided into three areas: the past, present, and future. So I will discuss all of these issues in some detail, and since this is a colloquium-like talk, I will not go into much of the calculational detail, but rather I will mostly content myself with a review of the earlier works and what are the kind of works that are going on, and try to give you a physical input of the present status of this particular research area without going into further mathematical details. So these works are mostly done from PhD students at IIT Gandhinagar and also at Jamia, along with some project students at ISCS, so whose names I have listed below. Uh, Yeah. So let us start with a brief outline of the talk. So first, regarding the past part of the talk, so we will try to discuss why we need this cosmic censorship conjecture and how we can see its validity. So as I mentioned, this is a conjecture, so it's not a proven theorem. So therefore, one would ask, are there any counter examples to this? Then in the present situation, I will try to connect this up with the black hole quasi-normal modes and try to provide certain evidence for its violation. And this is where things will become interesting because there will be a close connection of the sort of mathematical aspects of the cosmic censorship conjecture with the quasi-normal modes of black holes, which I believe would be quite interesting to the gravitational wave community. And finally, I will discuss about some future plans and what one can do if we want to include quantum fields into the picture. So I will be sort of brief in the future part, but I hope it will give you some idea about where this field is going in the future. So let us start with the past results. So just to begin with and to get things sorted out, there are two versions of the cosmic censorship conjecture. One is the weak cosmic censorship conjecture, and second one is the strong cosmic censorship conjecture. So I will be mostly talking about the strong cosmic censorship conjecture, but just to give you a flavor, let me briefly discuss about the weak version. So the weak version effectively asserts that there will be no naked singularity. So if there is a gravitational collapse and it forms a black hole, then the central singularity will always be hidden by the event horizon and some external observer cannot see it. So all this, I mean, as I will discuss, the strong version as well started by the work of Penrose, just like the weak version. And this reference that I have given, it was published as a golden oldie article in GRG, sort of gives you a nice flavor of how these ideas came along. So in most of the discussions about the weak version of the cosmic censorship conjecture, people try to look for counter examples to them. So the most famous example is to look for an extremal or near extremal charged or rotating black hole, and then throwing some additional charged particle or some rotating particle so as to overcharge or overspin the black hole. So a very nice discussion of this has been appeared recently in this paper by Source and Wald, where they use the covariant phase space formalism to describe how one can argue in favor of the weak version. Even though there is another recent work which I have also cited here, this Eperon et al. Paper, where they discuss some sort of a massive scalar field in a curved black hole, and by incorporating super radiant instability, they could cook up a situation where there is seemingly some violation of the weak version. So that sort of gives you an idea. And regarding this weak version, Professor Naresh Dodich here and Sudipto Sarkar from India, IIT Gandhinagar, they both have done several works in this area, so they are experts on this field. But I will not go into the weak version of this theorem. I will just talk about the strong version. And the strong version asserts that if you start from an initial data and you evolve it forward in time, then it cannot be extended outside the domain of dependence. I will just describe what the domain of dependence is, but the best description can be found in these two books, one by Wall, the other by Hawking and Ellis. So this gives you a picture of the domain of dependence. So let us start with, I hope you can see the cursor here. So you start with a surface which I have just written as sigma over here, and the boundary of which is referred to as B of sigma. And the domain of dependence of this hypersurface sigma, or to be precise, the future domain of dependence, corresponds to the set of points from which, if you draw the past null cones, they are always within the sigma. So as an example, you consider the point P over here, and you are drawing the past null cone, which corresponds to the blue cone in the figure. And you can see that it intersects sigma over a circle, and that circle is completely within sigma. So that means what is going to happen at P at a later time is completely determined by what you fix on the hypersurface sigma. On the other hand, there is a point Q which is outside the black light cone, and if you draw the past null cone from Q, it sort of gives you the red colored cone, past null cone from that point, and you see that the part of it lies outside sigma. So that means what is going to happen at Q is not uniquely determined by initial data on the hypersurface sigma. So this is what we meant by domain of dependence, that given hypersurface sigma, you consider a set of points from which, if you draw the past null cones, they should fill this hypersurface sigma. So that's why the black cone corresponds to the future domain of dependence of the hypersurface sigma. So this particular idea will play a central role in the discussion of the cosmic censorship conjecture. Now let us discuss a few reasons why we need this conjecture. So as you can see that this is about evolution of GR, and the strong cosmic censorship effectively ensures that general relativity is deterministic in nature. Or in other words, if I give you initial data on a t equal to constant hypersurface, as is normally the situation, and you evolve it forward in time, then you should be able to predict the nature of this space-time at a later time, at a later instant of time. And this is what we mean by deterministic, that is, given initial data, you can predict the future. There are several other ways in which this can be casted. So one possibility is to say that given an initial data on a Cauchy slice, the entire future can be determined. Or in other words, you can say that the evolution in general relativity generically leads to globally hyperbolic spacetime. These are all sort of equivalent of one another, but I will just stick with the first one, that the strong cosmic censorship ensures the deterministic nature of evolution in GR. So after all this mathematical thing, let us try to understand it through some examples. I will discuss three examples. The first one is the most simplest case, that of the Minkowski spacetime. So this is a Penrose diagram. So in Penrose diagram, normally what you do, you start from the original manifold, which includes the points at infinity, and then you use some coordinate transformation involving tan inverse kind of functions, which takes infinity to a finite point, and as a consequence, you get this diamond-shaped region. There are several points which I have marked. The point I plus corresponds to t equal to infinity, the point I minus below corresponds to t equal to minus infinity. The point I0 stands for spatial infinity, or r equal to infinity if you like, or x equal to infinity. The line, so this null, these are 45-degree lines and these are all null. So this line, which is denoted as stripe plus, corresponds to future null infinity, and the line stripe minus corresponds to past null infinity. And you can see several blue surfaces in this diagram, and all of these are Cauchy slices. So these are the initial t equal to constant slices. So you can think of a time which is running from I minus to I plus, and each of these surfaces corresponds to t equal to constant surfaces in some sense. Now, suppose you want to consider that, suppose I have given initial data on one of these Cauchy slices over here, and I ask you what is going to happen at this point P, which is in the future of that point, of that surface. So to see that, you can draw the past null cone emanating from P, so which will encapsulate the, which is denoted by the black one over here. And you see that it intersects the original initial data hypersurface in a, which would be a subset of it. Because you can see that from this point to this point is a smaller region compared to the full hypersurface. So that means given initial data on this hypersurface, you can explicitly predict the what is going to happen to the point P. And this is sort of the standard practice that you use when you evolve things in Minkowski spacetime. So for example, if you're considering a field theory in Minkowski spacetime, you give phi, the field phi, take a scalar field for example, and its time derivative on this on a particular hypersurface. And then you can evolve it forward in time using the evolution equation, and you can explicitly tell me what is going to happen at the point P. Interestingly, you see that if you take any one of these Cauchy slice, any one of this blue curve, the future domain of dependence is sort of the one above that surface up to the point I plus, while the past domain of dependence is the one below the surface and it's actually up to I minus. So if you consider the union of the future domain of dependence and the past domain of dependence, it covers the full space-time. So that means that the cosmic censorship conjecture, which tells that given initial data on a hypersurface, if you evolve it forward in time, then it is always within the domain of dependence. So that's exactly what happens for the case of Minkowski spacetime. So you give initial data on any one of this blue curve, evolve it forward in time, and you see that it is always within the Minkowski light cone. That means it is always within the space-time domain, or which is the domain of dependence of the initial hypersurface. So the cosmic censorship conjecture is respected. Let us now discuss the second and another very familiar example, that of the Schwarzschild spacetime. And again, I am discussing about the conformal diagram of it. So the I plus here again corresponds to t equal to plus infinity. I minus corresponds to t equal to minus infinity. I0 is the r equal to infinity. Scribe plus stands for the future null infinity, and scribe minus is the past null infinity. Just like in the case of Minkowski spacetime. The only difference is the space-time sort of ends at this red labeled line, which are the singularities. This is the future singularity, and the one below corresponds to the past singularity. And the red lines, so sorry, the blue lines over here, they correspond to the space-like hypersurfaces, just like in the case of Minkowski spacetime. And the other 45-degree yellow lines, they are the event horizon. So here also, if someone asks the same question, that suppose I have a scalar field living on the Schwarzschild background, and I want to evolve this scalar field forward in time, then what will happen is that, I mean, you suppose you want to know it, what will going to happen at some point P in the future. Again, you draw the past null cone emanating from that particular point, and you will see that it is completely within any one of these blue Cauchy surfaces. So that means that the evolution or the future evolution is uniquely determined given the initial data on one of these blue Cauchy surfaces. Again, if you take any one of these blue surface and you say, I want to draw the future domain of dependence, that means set of all points whose past light cone is entirely within that hypersurface, you will see that it actually fills the full space-time. So just like in the case of Minkowski spacetime, for Schwarzschild spacetime as well, the union of the future domain of dependence and the past domain of dependence gives you the full Schwarzschild spacetime. Therefore, even for Schwarzschild spacetime, the cosmic censorship conjecture is identically respected. But the situation changes drastically for the case of a charged black hole. So what I have drawn on the left is the Penrose diagram for a charged black hole. So this I plus, I zero, I minus, they stand for the standard thing I have discussed before. And it's actually an infinite set of diagrams. So let us not go into the top part. Let us concentrate on the square box over here and these two singularity regions. So these are now time-like singularity, which were space-like for the case of Schwarzschild. Now, suppose you have some particle which is starting from point 1 on one of these Cauchy slices. So it joins this I0 to the other I0, which is the red colored curve. Then the observer goes on and it hits at point 2, which is also on a Cauchy slice. And as you can see that what is going to happen at point 2 is entirely determined by the hypersurface 1, because if you draw the past null cone, it is completely contained within this region, within the first hypersurface. However, it can cross the violet colored line, which corresponds to the Cauchy horizon, and then it can reach point 3. And that is where all the problem starts to grow. So if you draw the past null cone from the point 3, you see that one part of it is certainly contained within the initial red light cone, red hypersurface, but there is another part of it which is sort of intersecting the singularity. Therefore, if I ask you what is going to happen or what would be the future of the observer at point 3, you cannot say it uniquely based on your initial data on the red hypersurface, because there can be some events happening in this region beyond the Cauchy horizon which can influence the event point 3, while those are nowhere encoded into the initial hypersurface drawn from I0 to I0. So that is why the initial data on a Cauchy surface, and if you evolve it in the future direction, then you cannot predict what is going to happen beyond the Cauchy horizon uniquely. So this is a serious problem, and people can sometimes say, well, this is for a charged black hole, so why should we care? Because charged black holes are astrophysically not a viable option. Astrophysical black holes do not have charge. But it turns out that this particular argument has absolutely nothing to do with the fact that black holes have charge. Even if black holes had rotation, the Penrose diagram, at least the part which interests us, would remain almost identical. The only change would be there would be an additional sector beyond the r equal to 0. Because unlike for Reisner-Nostrom, for curved black hole, r equal to 0 is a ring singularity which you can cross and go beyond r equal to 0. But the particular problem that I mentioned, that at point 3 you cannot predict what is going to happen to the particle given initial data on the hypersurface 1 remains true. So this suggests that there is possibility of breakdown of predictability of Einstein's equation. So as I mentioned, that for charged black hole in general relativity, the evolution beyond the Cauchy horizon cannot be predicted, and an identical conclusion holds for rotating black holes as well. And as rotating black holes are very common in astrophysical scenario, this suggests that predictability of GR breaks down. And it's a very serious problem. That means that even for the most simplest cases in GR, namely for black holes, we cannot predict what is going to happen when a particle just falls inside the black hole. And it's a serious problem. Of course, I mean, people can argue that we really have not seen black holes, whether there are black holes or exotic compact objects. These are some other debate. And of course, for exotic compact object, there are no Cauchy horizon. But in the context of black hole, which I believe most people will believe exists, the problem persists. And the prime reason for this to happen is that the space-time is regular at the Cauchy horizon. So this is something people have realized long back. It started again from the work by Penrose. But just to show you the particular point which people had thought about, I am just taking this figure from the paper by Chandrasekhar and Hartle. So it's a very illuminating paper on this topic. So what they have done, so this is again the part of the Penrose diagram of the Reisner-Nostrom black hole. So this is the event horizon, the line CD, while the line EC or EC prime, that corresponds to the Cauchy horizon. And suppose there is a static observer doing nothing, but he has some sort of a light source and he's sending out light to infinity. So therefore we have light rays which are going at 45 degrees to Spry plus. But due to presence of gravitational potential, some part of it will be backscattered and it will go inside the event horizon. So as this figure suggests, that you see that as the light, as the observer progresses closer and closer to I plus, this light ray sort of accumulates near the Cauchy horizon. And one may expect that the total energy density due to this light ray will diverge near the Cauchy horizon. And this is primarily due to the infinite blue shift at the Cauchy horizon. So if the energy density diverges, one would expect that a back reaction due to this energy density will render the Cauchy horizon unstable. So this is precisely what Simpson and Penrose in their paper in IJTP they tried to propose. But it was most beautifully shown in this paper by Chandrasekhar and Hartle in 1980. So what they did, they considered a scalar field living in a charged black hole spacetime. So you can consider an electromagnetic field or gravitational field. It really does not matter. The calculations go through. And they computed the flux due to the scalar perturbation, which is crossing the Cauchy horizon. And they found that the behavior goes as exponential of kappa minus. Kappa minus is the surface gravity at Cauchy horizon, and kappa plus is the surface gravity at the event horizon times v, where v is the retarded advanced time, null time coordinate. And you see that this diverges as v goes to infinity, which is sort of evident from this exponential behavior of the function. This suggests that the flux diverges near the Cauchy horizon. However, the perturbation itself remains finite, which is very interesting. So what happens is that if phi is the scalar field, then phi is finite on the Cauchy horizon, but the flux corresponds to first computing the energy momentum tensor, which involves something like del v phi, and then contracting it appropriately, which diverges. So this suggests that this first order perturbation, so this is a first order perturbative calculation, this will source the second order perturbation, because when you are computing the second order effect in a perturbative scheme, the first order is the source for the second order effect. And if the first order effect, the source from the first order effect diverges, then one expects that the second order effect will sort of go to infinity as well, and therefore the perturbative approach itself falls down. So Chandrasekhar suggested that, well, in the perturbative approach, most likely this is as far as we can go. We can show that the flux due to the perturbation diverges at the Cauchy horizon. But what is really happening there has to be ascertained by doing a non-perturbative approach, because we cannot trust a perturbative expansion if things diverge. So this is a program which was taken on by Poisson and Israel, which I have just cited below, the PRL paper, and it was further elaborated in the paper by Ori. So what they considered is a very simple scenario, and it's a fully non-perturbative. So they did not consider any perturbation. So they considered a collapsing charged matter, which is collapsing and forming a Reisner-Nordstrom black hole. And at the same time, there are two regions. One is the collapsing region, and there is a black hole region after the collapse has happened. And after the collapse has happened, there is an influx of matter into the black hole. So therefore, they are sort of matching a charged Vaidya-like solution outside to a charged matter collapsing inside. And they could get a particular solution by using appropriate junction condition on the surface. After they have obtained that, what they showed is that if you only consider an influx of matter, then there is absolutely nothing funny going on at the horizon, at the Cauchy horizon. In particular, the mass function. In the Vaidya solution, they consider the charge of the Reisner-Nordstrom black hole to be fixed, but they consider the mass to be changing with time, and that's what, or some variant of that is what they call as the mass function, that remains finite. So there is absolutely nothing which is divergent at the Cauchy horizon. However, they realized that this is not a correct model to describe the scenario, because as the matter is going inside the black hole, there will be backscattering effect. So when they considered the backscattering due to the gravitational potential inside the event horizon, they could actually show that the mass function diverges. And it diverges in exactly the same manner as the flux law I have depicted here shows. It diverges exponentially with respect to this parameter V. And that is why the name mass inflation comes in, because in inflation, the scale factor sort of grows exponentially. Here also, as V goes to infinity, that is, you are going nearer to the Cauchy horizon, the mass function also goes to infinity. That's why the name goes by the mass inflation. And they explicitly demonstrated that certain curvature invariants diverge on the Cauchy horizon. So people were very happy in the sense that, well, so you do not have to worry about Cauchy horizon. Actually, our universe does not go beyond Cauchy horizon. They end at the Cauchy horizon due to this curvature singularity. But there were some problems, and this is what was pointed out by the Ori, and this is what I will discuss in the next slide. So before going to that, this is the left-hand side is the Penrose diagram of the setting, which was considered by Poisson and Israel. So you can see that this particular stapled kind of a curve corresponds to the join of an incoming matter and an outside Vaidya solution. It's Vaidya because there are matter fields which are going into the horizon, and these are like apparent horizons which at late times coinciding with the event horizon and so on and so forth. And this is the Cauchy horizon whose evolution we are concerned about due to a influx and due to a scattering of it. So they have just shown it here, but it should also be in this direction. So in that context, you can show that the mass function diverges on the Cauchy horizon. But the singularity at the Cauchy horizon is weak. So this is the finding of the Ori paper. So why so? Because there are two aspects of singularity. So if you can show that the Riemann tensor diverges, that's a very good indication that there is a singularity. But there is another point that the tidal part of the Riemann tensor should also diverge. Or in other words, the geodesic deviation equation, which tells you that if you have two massive particles, I mean, it can be massless as well, which are falling into a black hole, will be tear apart by the huge gravitational force near the singularity. This is true for Schwarzschild, or this is also true for near the singularity of Reisner-Nordstrom, but this is not true near the Cauchy horizon. So this is what Ori showed. He showed that the tidal part of the Riemann tensor remains non-singular. And the reason this happens is that even though the mass function diverges, if you integrate it over the full affine distance on the Cauchy surface, it actually remains finite. So therefore, the version of the cosmic censorship conjecture, which says that you cannot go beyond the Cauchy horizon in naive terms, is actually not true. Because there can be observers who can actually cross the Cauchy horizon and go to the other side, because they would not encounter any divergent tidal force acting on them. So this is where the problem again starts. So there are two aspects of this problem. One is that one need not worry about curvature. So that means metric, connection. These are not necessarily continuous across the Cauchy horizon, but they should exist nonetheless because a particle can cross through. So what are the conditions that I have to impose on our metric or on our manifold structure so that I can prohibit that? So that particular condition was suggested by Christodoulou. So this is what people in present time says by the strong cosmic censorship conjecture. This is the version due to Christodoulou. So they say that it is impossible to extend this space-time across the Cauchy horizon, where the Christodoulou symbols are square integrable and the matter fields belong to the Sobolev space. So the Sobolev space is nothing but a set of functions which themselves and their derivatives are square integrable. So effectively, this ties with the square integrability of the matter fields and the metric and the Christoffel symbol. So this was first tested for asymptotically flat black hole solutions in GR in the set of papers that I have cited below, mostly by the group of Mihalis Defermos at Princeton. And they have found that the above version of Christodoulou is actually respected. And the reason it is respected can sort of be guessed from a very physical intuition, is that if we have an asymptotically flat space-time, then by Price's law, the gravitational perturbation or even scalar or electromagnetic perturbation, they decay only as a power law. While near the Cauchy horizon, there is an infinite blue shift. That means they amplify the radiation exponentially. So there are two effects which are competing. One is the power law decay and the other one is an exponential growth. Now, of course, it's the exponential growth which is going to win at the end, and therefore the strong cosmic censorship conjecture will be respected because things will diverge at there, the tidal part will also be divergent, and therefore you do not have to worry about extending beyond the Cauchy horizon. But let me briefly comment on from where does this square integrability condition comes from? Or what do we mean by extending beyond a region which has divergent Riemann tensor? So this comes as a weak solution extension. So these are sort of well known in the shock wave literature, because if you have a shock wave, then things are not differentiable but they do exist under integral. So that's what we mean by weak solution. Just to drive the point home, you consider a scalar perturbation phi and take it to be massless. I mean, you can put a mass as well, it really does not matter. So it's a box phi equal to 0 or box phi plus m square phi equal to 0. Then if you think of this as, if you think of this as sourcing the Einstein equation, you will sort of get a differential operator, which could be a box operator and so on, acting on the second order metric perturbation, h mu nu 2, and that will give you 8 pi g times the energy momentum tensor arising out of the scalar field phi. Now, as I just said, that neither phi nor h mu nu are continuously differentiable because curvatures diverge. So this equation does not make sense as I have written here. But the above equation, if it makes sense in the following integral form for any well-behaved tensor psi mu nu, which is a C infinity function and which has a well-behaved boundary property, so that when I am going from d on h to mu nu to the derivative operator acting on psi, I have performed some integration by parts, and you assume that psi is such that those boundary terms can be ignored. In those contexts, this particular solution, this H2 mu nu and this phi are called weak solution. So what Christodoulou's conjecture actually says that you cannot extend the metric or the connection even weakly across the Cauchy horizon. So the first equation, as we see, does not hold. This is of course not true because both sides are divergent. And what Christodoulou asserts is that even the second equation, which is an integral form, is also not true, because both sides should have some particular regulatory behavior. So suppose now for the moment being that both sides are finite, then what are the conditions on the phi as well as on the gravitational perturbation? So that means that integral of psi mu nu into t mu nu has to make some sense. And t mu nu consists of phi and its first derivative. So if it is a massless field, then t mu nu is just derivatives of phi. If it depends on mass, then t mu nu goes as m square. There is a term which is m square phi square. So you see that this equation will only make sense if phi and its derivatives are square integrable, because t mu nu depends on phi and its derivative as a square of them. So it is del mu phi, so it's like del v phi whole square. Or if there is m square phi square, then there will be a phi square term within t mu nu. And this is exactly what we mean by the Sobolev space H1 local, that set of functions which itself and their derivatives are square integral. For gravitational perturbation, on the other hand, I can replace this capital phi by the first order gravitational perturbation h mu nu, because first order gravitational perturbation will sort of source the second order gravitational perturbation. So that means that h1 mu nu and its derivative should be square integrable. And what are Christodoulou symbols? Christodoulou symbols are nothing but the first derivative of h1 mu nu. Therefore, this condition asserts that if weak solutions had to exist across the Cauchy horizon, then Christodoulou symbols had to be square integrable and matter fields had to belong to the Sobolev space. As you realize by the statement of the Christodoulou's version, that this is exactly what he prohibits. So his theorem or his conjecture says that you cannot have square integrable Christodoulou symbols or matter fields belonging to the Sobolev space. So this was, I would say, the past part of the talk. So this is, as you can see, it was pretty, I mean, the last paper on this topic was around 2017. But after that, there were several other interesting development, which is what I will going to discuss in the present part. So let us go to the present. So as we know, in the context of cosmology, cosmological constant did play a very important role. It actually saved us and gave us a very nice avenue to address the late time acceleration. I mean, modulo all the current ambiguities and confusion. But I mean, as of now, it's lambda CDM is still one of the best models to describe the late time acceleration. But for the case of cosmic censorship, or for black holes, so to speak, lambda actually did not come for rescue. So this happened because of this very nice work by Hinz and Vasi in 2015, where they actually showed that for asymptotically de Sitter spacetime, the gravitational perturbations do not decay as power law, but they decay exponentially, with the exponential factor alpha depending on the lowest lying imaginary part of the quasi-normal mode frequency of the black hole. So this is where the cosmic censorship gets intertwined with the black hole perturbation, or in other words, the quasi-normal mode frequency spectrum of a black hole. So you see now there are two effects. One, the perturbations which are decaying exponentially, and there are perturbations which are growing exponentially due to blue shift. Therefore, there is a parameter alpha, there is a parameter kappa minus. And you can actually extend things beyond the Cauchy horizon if this alpha by kappa minus ratio satisfies certain criteria. So this is what was pointed out by Vitor Cardoso and collaborators, this paper in PRL in 2018, less than 2 years back, where they showed that if this ratio alpha over kappa minus is greater than half, then actually a perturbing scalar field at the Cauchy horizon of Reisner-Nordstrom de Sitter black hole violates Christodoulou's condition. So this is what they actually demonstrated, and I will try to discuss how this can be achieved. And there is actually an analytic way to arrive at this result, which is what I will discuss. So there are two approaches one can take at this moment. One can just do a numerical analysis and get all the quasi-normal modes and be done with it. But there are also very nice analytical tools available to compute the quasi-normal modes. So when I started working on this project, actually I did not knew about all these results. So I thought it would be nice to share this with you as well. So in this context, there are three classes of quasi-normal modes. One corresponds to the photon sphere modes. So these are classes of quasi-normal modes which originate from perturbation of the photon sphere and also known as the eikonal modes, or in the large angular momentum modes if you prefer. Then there are near extremal modes. So these are the quasi-normal modes which originate when the event and the Cauchy horizons coincide, almost coincide. And then there are de Sitter modes. These originate in the limit of small cosmological constant. So photon sphere modes are actually very interesting because you can compute the quasi-normal modes of them by a very nice, completely classical and analytical calculation without going into any of the numerics. And as I will show you in a few slides later, they matches very well with the numerical observation. So what you do, you effectively compute the trajectory of a photon in the equatorial plane, and you do compute the potential, effective potential it experiences. The photon circular orbit is determined by setting this effective potential to zero as well as its derivative to zero. And then you perturb around the photon sphere. So there is R photon sphere going to R photon plus a delta R perturbation. And you see that the perturbation satisfies this kind of an equation, which you can immediately solve. And you realize that this delta R actually grows exponentially with the affine parameter lambda. And this sort of gives us the fact that we are working at the maxima of the potential. And this gives you the instability time scale, which goes as the double derivative of the potential. On the other hand, if you do the same calculation using WKB, if you want to find out the quasi-normal mode, then again, since the first derivative of the potential vanishes, it means that I can sort of approximate it by a parabolic potential. And therefore, I can solve it in both the regions. So this is like the region 1, it corresponds to the region from photon sphere to infinity. This is sort of the photon sphere, and this corresponds to the region from photon sphere to the horizon of the black hole. These are in the retarded tortoise coordinates, so it goes to minus infinity at the horizon and plus infinity at infinity. And then you get the parabolic cylinder function as the solution, and you impose the appropriate boundary condition that it should be ingoing at the horizon and it should be outgoing at infinity. And you see that the imaginary part of the quasi-normal mode is precisely given by the double derivative of the effective potential. And in the last slide, we just saw that the double derivative of the effective potential gives you the corresponding instability time scale. Therefore, you get a very nice relation giving the quasi-normal mode of a black hole in terms of the angular velocity at the photon sphere, which sort of gives this the real part, and the imaginary part is completely determined by the instability time scale of the photon sphere. With that, you can immediately see that the computation of the violation of cosmic censorship becomes very simple. So the imaginary part of omega, that is n plus half lambda, as you can see from here, that imaginary part of the quasi-normal mode frequency. So the alpha is the lowest lying one. So lowest lying means you put n equal to 0. That would be the lowest lying imaginary part. So it's just lambda ph over 2. and you substitute it in the definition of beta, which is alpha over kappa minus, or mod alpha over kappa minus, and it's actually lambda pH by kappa minus greater than 1. So kappa minus is completely coming from your metric. That is, if I give you the structure of the metric, you can compute kappa minus. Lambda pH is the double derivative of the effective potential of the photon sphere. So you do not have to do any numerical analysis. Just by computing these two purely classical quantity, which are pretty easy to compute, you can assert whether things are being violated. Now, for the other modes, just as a passing by, I mentioned that for near extremal mode also you can do it, because this can be translated to an ADS kind of a solution, and then you can solve it in terms of hypergeometric function, and if you put appropriate boundary condition, you get the QNM. So these are the near extremal modes QNM, and similarly for the de Sitter case, it's only the asymptotic structure that matters, and with appropriate boundary condition, you get the de Sitter QNM. So this part was sort of straightforward. Now I come to the one of the main results that which explicitly shows that the strong cosmic censorship is violated. So what I have plotted here is beta versus q over q max. So q by q max equal to 1 corresponds to the extremal limit. So that's when the black hole is extremal. And this is done in 4 dimensions with a certain value for the cosmological constant lambda. The blue one corresponds to the photon sphere mode, the red one corresponds to the near extremal mode, and the green one corresponds to the de Sitter mode. So you see that the lowest value of beta is what we should take. So the lowest value of beta is governed by the photon sphere mode up to this point, and then the near extremal modes take over. You can also understand why we call it near extremal, because as you can see that when the near extremal modes took over, q by q max is very close to the value unity. And as I mentioned, beta greater than half denotes a violation of the cosmic censorship. And you can see that there is a point where beta becomes greater than the value half. And there is a certain parameter space of q by q max, which is allowed where the beta can be greater than half. On the other hand, you see very interestingly that beta can not be greater than unity, because if beta is greater than 1, then it's much worse, because then it says that you can even analytically continue it across the Cauchy horizon as in a continuous manner, which is worse than what Christodoulou said. But at least this figure explicitly tells you that the Christodoulou's version of cosmic censorship conjecture is violated for Reisner-Nordstrom de Sitter spacetime, which is a serious issue, because then it tells you that for any asymptotically de Sitter spacetime, you cannot predict what is going to happen in the future, because the one that asserts that determinism in GR, namely the strong cosmic censorship, is actually violated. Now, this we have tried in various other contexts. I will just give you an idea. Yeah, I have sufficient time. So so this is the case of a higher dimensional Reisner-Nordstrom de Sitter black hole, and in this case also all these modes can be analytically as well as numerically computed. And this is sort of the figure that you get. So I have plotted beta with q by q max in all of them. The plots in the first row corresponds to d equal to 4, second row corresponds to d equal to 5, and third row corresponds to d equal to 6. And as we have observed that as you increase the space-time dimension, the q by q max, the value at which it crosses 0.5, sort of becomes smaller and smaller. That means you have a larger parameter space available where the violation happens, and this is why we meant it to be a stronger violation. Another interesting point. So for smaller values of lambda, for example 0.01, is the de Sitter mode which dominates. This is what I told you, that when lambda is small, is the de Sitter mode which dominates, or which is important. As lambda becomes larger, say 0.05, is the photon sphere mode that dominates, as you can see in both the plots. And secondly, when q by q max becomes very close to unity, that is very near extremal regime, it's always the near extremal mode that dominates. So that sort of gives you an idea for these names, because de Sitter modes when lambda is small, near extremal modes when the black hole is very close to extremality. So in that case, beta is dominated by the near extremal mode. For small lambda, it is dominated by de Sitter mode. And the same holds true in higher dimensions as well. The second thing that we tried to understand was for black holes on the Brane. So this is mostly following the work by Professor Tadich and also Harvey Rial. And the metric takes the form as I have shown here. So here 1 minus 2m by r and q square over r square is the standard contribution that you get for a Reisner-Nordstrom black hole. This q parameter sort of tells you about the inter-brane separation, because I am doing some higher dimensional calculation over here. This alpha q4 comes from some junction condition, and lambda by 3 r square is obviously there because this space-time is asymptotically de Sitter. So in that context, if I again plot the same set of curves, so the first column corresponds to q equal to 0, second column corresponds to q equal to 4, 5, and third column is 0.9. So you see that the value of q by q max where the violation happens becomes larger and larger. That means that these black holes have a smaller parameter space for the violation to happen. So there are violation becomes weaker as you increase the value of q, which means you decrease the interbrane separation. And again, here you see that for smaller values of lambda, it is the de Sitter mode that dominates, the green one, while for larger values of lambda, it is the photon sphere mode which dominates, while ultimately it is always the near extremal mode, the red one, which dominates in all of these plots. Now the next question, and this is one of the most puzzling feature, is that for rotating black hole, what happens? It turns out that for rotating black holes, the violation does not happen. So as far as I know, there are no reason people have sorted out, no intuitive feeling why it happens for rotating black hole, but it seems to happen. So we have again plotted beta with respect to a by a max, because for rotating black hole, the rotation parameter is of importance. And you can see none of this, including D4, D5, or D6, they process the value 0.5. When a by a max is almost 1, that is very near extremality, it sort of asymptotes to the value 0.5, but it never crosses it. So therefore, the cosmic censorship conjecture is respected for rotating black hole. So at least from astrophysical perspective, this should not hinder our progress, because rotating black holes are not plagued with these instabilities. I mean, with this problem. But just out of curiosity, we have also studied what happens to the static black holes with higher curvature term. So if you include higher curvature term, people sometimes believe that they may smooth out the singular behaviors of GR. Or if you think of GR as a low energy effective action, then there has to be higher curvature term supplementing it. So the Gauss-Bonnet seems to be the most natural one in 5 dimensions. And if you consider with cosmological constant, this is the structure of the metric. This should be d omega 3 square. I'm sorry, this should be r square d omega 3 square, because it's in 5 dimensions. So if you take the small alpha limit, for example, over here, then you can actually retrieve back the d-dimensional solution that we had derived earlier. But all of this sort of goes through hand in hand, and we get back the following table. So this is what I was trying to tell you. So you look at the, I will come back to this red colored boxes in a moment. So you look at the L equal to 10 mode. So this particular, the last but one column and the last column. In the last but one column, I have presented the result from numerical analysis, while in the last but one column, I have presented the result from just analytical computation. And you can see that the analytical result is actually accurate in most of the cases, up to 2 places after decimal. So it shows you that analytical computation gives you a very nice handle about the quasi-normal modes, or this is the imaginary part of it. In the context of photon sphere. So this L equal to 10 means large L value, which is the Eikonal limit in some sense. So these are the photon sphere modes. The L equal to 0 corresponds to the near extremal mode, and L equal to 1 are the de Sitter mode, which you can just see from here. So you see when lambda is small, 0.06, then it's always for 2 values of q by q max, it is the L equal to 1 mode, which is the smallest. So here compared to other two. So that is why the de Sitter mode dominates when lambda is small. But then suppose I increase lambda to 0.1, and then I go to a near extremal regime, which is 0.995 for the value of q by q max. Then you see that it's the near extremal mode, which is the lowest lying value for the imaginary part of the q. So this is what I have been telling from the beginning, that this description or the difference that we pointed out, de Sitter, near extremal, and photon sphere, they are pretty much clear from this particular table. And the analytical result is very much in unison with the numerical analysis as well. So this is the plot for the case of higher dimensions. So as you can see that the first column, these are for alpha equal to 0, that is Einstein gravity in 5 dimension, while the next column is for alpha equal to 0.1 and third column is for alpha equals to 0.2. So in all of them, as you increase the value of alpha, the value at which it crosses the zero point 0.5 barrier in decreases. So Q by Q max decreases. That means you have more and more region accessible to you of the parameter space where the violation happens. And as I mentioned, this is what we call as the stronger violation of the cosmic censorship conjecture. We have also tried it out with pure Lovelock theories motivated by the work of Naresh. And in that context, we saw that the violation of the strong cosmic censorship is actually stronger in pure Lovelock theories in comparison to GR. Because I think this plot should drive the point home. So you have a beta parameter which I'm plotting, and I'm plotting it with Q over Q max. So you see that the blue one corresponds to the Einstein case, and the other one, the brown one, corresponds to pure Gauss one in the same dimension. So therefore, it crosses the value 0.5 at a much smaller value of Q by Q max compared to that of pure Einstein case. So for pure Lovelock theories also, it seems that the violation is stronger compared to that in GR. And this is just another way of depicting the same thing. As the last bit of this current or present analysis, I have just presented the results with conformal coupling. So in the presence of conformal coupling, and there is also a Nash charge, but let us forget it for the moment. So here, the most important feature, I would like to take a look at the last figure of the second row, where you can see that the near extremal mode even crosses the value 1. So the value of beta becomes greater than 1 for the near extremal mode, and which is also true for other figures. So this is again a very serious trouble. What this tells you is that it's not that the perturbations violate the Christodoulou condition. Of course they do. But in addition, you can actually continue the perturbations continuously over the Cauchy horizon, which is another very puzzling feature, because that shows that even some further stronger version of the cosmic censorship is violated. So this is sort of very perplexing to most of the general relativists, and as far as I can see, there is no unique answer coming from the classical analysis so far, because everyone is trying to do it in various circumstances. So by the way, I just discussed the situations I have considered myself, but there are several other scenarios considered by the Harvey Rial, Vitor Cardoso, and other groups, including Sahar Hod, but those I have not touched upon. I just give you a brief glimpse about the kind of works that I have done here with references. Now in the future, so this is the present status, and it seems very confusing that which direction should we follow, because it seems to be violated by many circumstances, and it seems to be even violated much stronger than we initially thought. So this is where the future part comes in, and in the future, people always hope for quantum effects to cure everything. So the initial attempts were actually futile. So what people try to understand is what happens when you consider, instead of considering g mu nu equals to 8 pi g t mu nu, you take g mu nu equal to 8 pi g expectation t mu nu. So this was first done by, again, Harvey Rial, Oscar Dias et al. In just about a year back. And they did it using the quantum stress tensor, so expectation T mu nu, for a three-dimensional rotating BTZ black hole, because it was a simple enough system to compute this object. And they found that the T mu nu, the value of the quantum stress tensor, renormalized of course, is finite over the Cauchy horizon, and therefore you can extend it. So this came as a very surprise, and people were very worried that then it seems that even addition of quantum fields is not going to save the situation. But people still try to see what happens if I consider a four-dimensional black hole. So I will come back to this figure in a moment, but this was done by the paper by Hollands, Wald, and Zahn, two consecutive papers. The last one appeared in the last month by Hollands himself. And what they computed is in four-dimensional computation of T mu nu, which is pretty complicated. And if there are questions, I can discuss about it. But it can be done more easily in two dimension, using the fact that there is something called conformal anomaly in two dimension. And using that, what they found that if you compute this TVB, certain component of the energy momentum tensor, over the Cauchy horizon, and it is related to the corresponding value at the cosmological horizon modulo an additional constant factor which depends on kappa c square, that means surface gravity at the cosmological horizon minus surface gravity at the Cauchy horizon, square of both. And the capital C in this context is related to the conformal anomaly factor, so which is like 1 by 24 pi or something like that, depending on which field theory we're looking at. But this is just a approach in small v coordinate. But if you want to make further connection, you have to go to the global coordinate chart. This is the global coordinate chart for Reisner-Nordstrom de Sitter. So here the only difference is there is a cosmological horizon now, and that's why the infinity line has been shifted to this region. Rest is exactly identical to the Reisner-Nordstrom-Penrose diagram I have shown. So what you do, you have a small v coordinate, you change it to capital V minus over the Cauchy horizon. Again, you have a small v coordinate, you change it to Vc over the cosmological horizon. And there are well-defined coordinate transformation relating the two. When you do that, you get the relation that I have written at the end. So the Cauchy horizon expectation value is related to a constant term which goes as 1 upon v square, and there is a TVV expectation over the cosmological horizon with certain power of v. Therefore, the statement goes that if you have quantum states which are Hadamard near cosmological horizon, which effectively means that this quantity TVV expectation is finite over the cosmological horizon, then you see that when V goes to 0, which is the limit to the Cauchy horizon, this stress tensor diverges. And it diverges because of this term C, and C is effectively proportional to H bar. So the divergence at the Cauchy horizon is a purely quantum mechanical phenomena or quantum field theoretic phenomena, if you wish, and it has absolutely no classical analog. So this is why I mentioned that light at the end of the tunnel, that because people believe that this is probably the way in which the puzzle with the cosmic censorship conjecture needs to be resolved. But again, this is for a very simple system for a conformally coupled scalar field, because only in that context some of the calculations can be done. What happens for more generic situations is not known. Whether the coefficient C can vanish at certain instants is also a an intriguing question. As the latest paper by Holland shows, there are certain places where the C can vanish. And if C vanishes, then it's presumably again the earlier statements will come true. So there are many open questions at this end. So I think I have almost running out of time. So I will just end with the concluding remarks. So first of all, I have tried to convince you that strong cosmic censorship conjecture is very important to uphold the deterministic nature of GR. And any violation of this conjecture sort of tells you that GR is not deterministic, which would be disastrous. For asymptotically flat spacetime, the Christodoulou's version of the strong cosmic censorship conjecture holds true, which is what we want. On the other hand, for asymptotically de Sitter spacetime, it is not true, and you can actually extend all the perturbations as a weak solution across the Cauchy horizon. Secondly, the violation is sort of ubiquitous. It's present in higher dimension, higher curvature theory, even with the presence of conformal coupling. And in some cases, it can even become stronger in comparison to the 4D case. Finally, the quantum stress energy tensor, the renormalized one, it actually seems to diverge at the Cauchy horizon, and hence is possibly responsible to save the day. So therefore, it's a very intriguing situation where a classical phenomena, a classical problem, seems to be curable by a quantum mechanical treatment of the issue by incorporating back reaction. But there are several technical hindrances because computation of this tensor is not an easy task, and there are many other subtleties involved. So with this, I think I will just thank all of you for your kind attention and patience. So I will now open for questions.
Thank you very much, Sumanta. That was a great talk. Can you please raise your hands? Already there are a couple of hands up. And if you raise your hands in the participants window, I will start with Shukanta Bose asking his questions. Unmuted.
Hi,
Shukanta.
thanks for the nice talk. My question is on something you described towards the end, that maybe there is some hope that quantizing the fields can come to the rescue
Yes.
of preventing violation of cosmic censorship of some form. Yeah, that's right. So, and it's good to see that H bar has an explicit role to play in this, the continuity theory. My question is, First of all, okay, this was demonstrated in 2 dimensions. So I wanted to know specifically what kind of 2-dimensional spacetime are they considering? Is this a mini super spacetime model, or is it actually dimensionally reduced black holes? And a related question is, this also reminds me of some work in the 90s when Chopwick first found classically that you could have actually violation when you considered collapsing scalar fields, right? There was some initial critical configuration for which you could form zero mass black holes, but they would actually have a naked singularity. But then that was also resolved quantum mechanically. And one of my works also contributed to that, where we showed that the phase transition is such in this solution space that quantum mechanics prevents you from forming zero mass black holes. Actually, there's a mass gap in the transition across the critical set of parameters that find the initial configuration of the scalar fields. Do you see any connection between that kind of work and this resolution? That's the second question.
Okay. To answer the first question, in the 2 dimension, they effectively considered a dimensionally reduced black hole, in the sense that in 4D you have some minus f of r dt square plus dr square by f of r, and then r squared d omega square. So you effectively chop out the angular part, you just consider the tr sector of the space time, and then you compute this object. But the point is, they have also computed the T mu nu in 4 dimension, which is much more involved calculation. So there, the idea is as follows. I mean, I will just briefly state it. So the idea is that you start with, in 4 dimension, what you do a mode sum regularization technique. So you compute T mu nu, so you have all the components, and then you expand this T mu nu in terms of the modes, because T mu nu is nothing but del mu phi, and phi has a mode sum decomposition. So after you have done that, you know the modes from the Hadamard state near the cosmological horizon, related by a Bogolubov transformation to the modes near the Cauchy horizon. Therefore, you can relate the Cauchy horizon expectation value to the expectation value at the cosmological horizon. And this coefficient C, which is sitting here, would actually be some integral over the Bogolubov coefficient presented in certain way. There would also be some reflection and transmission coefficient associated with the mode functions, and those you can compute by solving what we call as a U1, confluent U1 differential equation, and you can do this explicitly. So interestingly, if you do this for the case of BTZ black hole, you explicitly get C equal to 0, which is why the original work by Harvey Rial did not find any divergence at the Cauchy horizon, because C identically vanishes for them. So it is not that it is only done in 2D, it can also be done in 4D, and in 2D it is for the dimensionally reduced black hole. Regarding the other point that you mentioned, I think there is some connection, but the point you are mentioning is about abhorrence of naked singularity, which is more related to the weak version of the cosmic censorship conjecture. Rather, what I am discussing here is the strong version of the cosmic censorship conjecture. So I think the result that you mentioned is a complementary to the strong version. As you said, in the weak version, in incorporating quantum effects, you can get rid of the zero mass case, and therefore you can save the weak cosmic censorship conjecture. Here also we are saying sort of the same thing, that by incorporating quantum effects, we are arguing that you can get, I mean, you can make the cosmic strong version of the cosmic censorship conjecture to hold true. Is that, does that answer your question?
Great, thanks. Anybody else? I don't see any other hands up. You give such a great talk that nobody has any questions. Akash. Who's Akash? Unmuted.
Yes. Hi, Sumanta.
Yes.
Yes.
So my question is, so is this always possible that this 1 over v square divergence will be able to compensate the exponential growth?
Yeah, no, see, the point here is not about the exponential growth. The point is whether this TVV is finite and how it is finite. So in the original case, what happened is that TVB is finite in the sense that there was this exponential of alpha minus the beta parameter, kappa minus kind of an object. But that is in the small v coordinate, you see. So if you translate small v to capital V, that parameter is actually hiding in the capital V to the 2 kappa c by kappa minus 2 term. So this is sort of the analog of the beta term. So you can see this kappa c by kappa minus is very close to the beta. So it's showing beta greater than 1 in some sense. So it's just a coordinate transformation. So whenever things are in capital V, if you translate to small v, you will get exponential.
Right.
So in that sense, this v square is like e to the minus 2v kind of an object. Minus 2 and all these things will also appear in the front. And that will always diverge, irrespective of whether there is the alpha by beta ratio greater than half or not. Because this has no dependence on any parameters of the black hole spacetime. So irrespective of that, it will diverge. When v goes to 0, or if you go to small v, this will become exponential and small v will go to infinity. So you
Okay,
just
thank you.
have to make the transformation from capital V to small v.
Great, thank you. Next, another hand up. Shomodeep, unmuted. Go ahead and ask your question.
Sumanta, hello. So,
Yes.
so this is actually a question I wanted to ask you a few days ago as well. So, in the first paper that Holland's Wald Zahn have did, where this TVV Cauchy they have calculated. So, the condition they have mentioned that, as you were saying, that the thing we need to check whether this capital C is 0 or not. So my question is, other than that, let's say for as they have calculated that in the cases where capital C is not 0, can we have a condition that kappa C equal to kappa minus?
Yeah, I mean, of course, in that case, it will be 0, but that would mean that the Cauchy horizon and the cosmological horizon has to coincide, which is a very unlikely phenomena. And I mean, it's very unlikely that these two horizons can coincide. So kappa plus equal to kappa minus means extremal limit, but this requires kappa C equal to kappa minus, which
Yes.
is very unlikely to happen, because
Okay.
this require kappa C to be equal to kappa plus equal to kappa minus, some kind of a relation like that, which would be just one point in the parameter space. And I mean,
Yes.
you know,
Yes. Yes.
measure 0 kind of a thing.
Okay.
Yeah, so
Okay.
that is
Great.
very unlikely. So C going to 0 is a more plausible condition.
Thanks. Naresh has a question.
Okay. Yes.
Naresh, I'm unmuting you.
Hi, Naresh.
Naresh, you're
Yeah,
unmuted.
yes, yes,
Yeah.
yes, Sumanta.
Yes.
As usual, excellent talk.
Okay, thanks.
Let me try to understand few things in my own simple way.
Sure, sure.
So, tell me that the existence of a Cauchy horizon. Okay, first condition to have a strong censorship violation is that Cauchy horizon must exist.
Yes. In
Right?
the unperturbed space-time. Yes.
Yeah, in perturbed space, this must exist. And then, now for that to exist, the overall gravity should change its sign from attraction to repulsion. Whether it is the contribution from the charge or whether it's contribution from the rotation.
Yes, yes.
Right? And now what you want is the second, for the violation not to occur, the Cauchy horizon should be singular.
Exactly.
So that's, so which in other way to say is that I am trying to understand whether can I understand in terms of the repulsive part becoming dominant.
Yeah, I think notice this part should answer it. Let me just go back to that slide. Yes. So you see that I think the repulsive part and the attractive part which you are mentioning is the power law versus exponential. So the
yeah, that's right.
So the exponential blue sheep sort of tells you that how repulsive it is, and the power law tells you how attractive it is in some sense.
That's right. Okay, yeah, that's right. In mass inflation, that yes, the blue shift is the real. Yes.
So for the power law, of course, power law is much smaller compared to the
The
exponential.
exponential, that's right.
But for
No,
asymptotically de Sitter case, it is the both are exponential. That is why the problem is present. So
well, very crudely, but the Sitter you have in some sense, but not at this level, but you are strengthening the repulsive part. Because the de Sitter itself gives you a repulsive, but that's for a large R.
yes, yes, larger. This is
But there
sort of
that, but here in the at the Cauchy horizon, that its contribution should be negligible, right?
Not really, because this there is the, I mean, the quasi-normal modes will still depend on alpha, because you see that when we determine quasi-normal mode, we have to put appropriate boundary condition. So
Oh yeah. Oh, okay. So the through the boundary condition that it will still come through.
Exactly, exactly.
And then there lastly the comment about your the violation being stronger in the pure Lovelock.
Okay, yes.
That is perhaps, but that one can understand, because that in the pure Lovelock gravity becomes weaker,
Okay, yes.
and hence that the violation will be stronger.
Yes, possibly that is the reason, yes. Because the power law behavior is different in the same
Yeah.
dimension. So
Yeah.
yes, that is, yeah.
Oh, okay. Thank you. Thank you very much.
Thanks very much.
Okay.
I don't know if there are any questions. If not, a wonderful talk and applause.
Okay, okay, thanks.
People can applaud you through Zoom if you can, but there's a difference between Bhaskara 3 and here is that we can't clap.